let's see another example, or maybe an application of linearity of expectation. And there are two things that I want to illustrate with this example. First of all, you will notice that in the statement of linearity of expectation, we did not say anything about these random variables needing to be independent or needing to be special in any way. It works for absolutely any random variables, which is different from some other things that we will see next time. So first of all, that there's no need for independence. And second of all, it is a nice use of this idea of breaking things down into smaller expectations to find things that are potentially very complicated to do directly. So let's do it. It is called the hat check problem. And the setup is this. We have n people who all check their hats when entering a restaurant. So they give their hats to the, little clerk person, who then stores them in the back. But the person who is handling their hats forgets to label them. And hands them back randomly when people leave the restaurant. So the hats have now gotten shuffled in some random way. And the question is, what is the expected number of people who get back their correct hat? So this is sort of the classic interpretation or statement of the problem. But we can say it in other language in sort of like a more formal mathematical way. Which is that we are asking for the expected number of fixed points of a random permutation of the set 1 through n. And just to be clear, fixed point means a number. So remember, a permutation is just an ordering of this set 1 through n. And if we choose some ordering of the set, a fixed point means a number in the same position as in the natural ordering 1, 2 through n. So for example, just to give a little example, a permutation of 1, 2, 3 might be, for example, 1, 3, 2. In this case, 3 has moved because it used to be there, and 2 has moved because it used to be there, but 1 is a fixed point because it is in the same position as in the usual ordering of the list. So you can interpret this as asking for the expected number of fixed points of a random permutation. You can also think of it as how many people get the correct hat back from the hat check, and that's the language that we will use when we are solving it. So the point is that it's not at all clear how to compute this directly, because the number of permutations, the number of ways to shuffle the hats of these people, is n factorial, which is a huge number. And it's not even clear if there's a good way to write down the number of fixed points of a random permutation. Basically, if you try to apply the definition of expected value, it's going to be an absolute nightmare. But linearity of expectation allows us to break it down. So let me say not at all clear. How to compute it directly. But using linearity of expectation, we can write x equals x1 plus x2 plus xn, where this random variable x is the one we are interested in, number of people who get the correct hat. And on this side, xi is 0 if person I gets the wrong hat, and 1 if person I gets the right hat. So again, as in the binomial example, you can see that x really is the sum of these variables. So this equation is true with the definitions that we've made, because every person that gets the correct hat adds 1 to the total. So when we add all these up, we will get the total number of people who get the correct hat. And furthermore, these things are much easier to compute the expected value. So this is sort of a clever way of breaking down the problem. And part of the cleverness, or part of the usefulness of linearity of expectation in this case, is to note the xi are not independent. So in the examples we looked at before, for example, the binomial distribution, a binomial random variable is a sum of independent Bernoulli trials. So in that case, it was independent. But in this case, these are very much not independent. Just to illustrate this, so for example, if x1 and x2, if all of them up to xn minus 1 are 1, which is to say these people all got the correct hat back, well, then there's only one hat remaining, and it must belong to the last person. So xn equals 1 also. And this is a witness to the fact that these are not independent, because it's saying if you know the values of these random variables, you can predict with certainty the value of this last random variable. So it is not independent from them. But, again, this is something that I want to emphasize, we can still use linearity of expectation. We made no assumption about independence. So now let's just go ahead and compute it. What is the probability that the ith person gets their hat back? Which is to say the probability that xi equals 1. Well, this person is getting a random hat back out of n hats, and only one of them is the correct one. So we can write this as 1 over n. Or if you want to be a little bit more precise, you can say that it is n minus 1 factorial divided by n factorial, which, as you can see, this will cancel out all of the things on the bottom except for the n, and you will get the formula over here. But this is more visibly counting the number of permutations fixing I, because this, if you declare that you're fixing one element, then you're essentially counting permutations of n minus 1 elements. And that is divided by number of permutations total. And we are computing the probability by just counting things because we are using a uniform distribution. So we are picking a permutation uniformly at random. So the expected value of xi, well, it has two outcomes, 1 and 0, and we know the probability of each. So it's 0 times 1 minus 1 over n. The probability of 0 is 1 minus 1 over n, because it needs to be the complement of the probability 1 over n. And then the other possible outcome is 1, the probability 1 over n. So the expected value is 1 over n. And this allows us to compute the expected value of x. It is the sum of the expected values of all of these guys, which is 1 over n for each of them. And there are n terms in the sum, so that's 1 over n times n, which is 1. So the expected number of people who get their hat back is exactly 1. And it's interesting that we didn't fix the number of people. This is for any number of people. So it is independent of n. The number of people that we expect to get their hat back from the hat check correctly is always 1, regardless of how many hats there were.